Thank you very much. So the session that I'm going to be delivering today is one that I've been doing at quite a few conferences around Europe, also around Sweden, where I'm based. And I love to understand how things work. My mum tells me that when I was a kid, I used to take stuff apart to figure out how it works. How does the cassette recorder work? The bigger question wasn't how it works, but how you put it back together and get things working. And ever since I've been working in programming, I've been interested in how algorithms work. How does machine learning actually work? How can we predict that an image is a cat and a dog? And then when GPT came along, it seemed like magic. There was something going on in there. It was almost like you were talking with a person and interacting with a person. And I was really curious about, what makes these type of models work? How can they appear to have almost a personality and something that we can interact with? So I spent quite a lot of time looking into how these large language models work. And this is kind of the current state of my understanding of large language models. This session changes a lot. I'm using a completely different code than I was using when I did this at GOTO in Amsterdam, rewritten all of the demos, and also had a bit of a deeper understanding about how these models work. It is complex. You're not going to get it fully in 45 minutes, but hopefully it will explain a bit about what's going on inside those models. A bit about myself. I'm based in Stockholm, Sweden. I work for a company called Active Solution. We've been inundated with clients asking us to build stuff where they can chat with their data using GPT and using GPT algorithms. So we're kind of actively involved with this. I've been playing around with AI for the past 6 years. Nobody else was interested in it for about 4 years. And recently, when GPT came along, everybody's interested in this. I do a lot with the community. I've been organizing conferences. I do stuff on YouTube. Involved in Coder Dojos with kids. And I'm also a Microsoft AI Most Valuable Professional. So I get to go to Redmond once a year and see the new stuff that Microsoft is doing with AI and give them feedback and so on. I'm quite active on LinkedIn, quite active on YouTube. I've got some videos on YouTube as well, if you want to check those out. Before I start, I'd like to thank the many other content contributors, not just YouTube, but other places who've been helping me to understand how this stuff works, especially people like 3 Blue, 1 Brown and Andre Kapathi and Centdex really helped me to kind of understand what's going on with machine learning. So we go into GPT and we ask it, how do I make cheese? And what it comes up with is it starts generating this answer about, cheese is a delicious, dairy product, blah, blah, blah. And it gives us those actual clarification. There's lots going on behind the scenes. So it's able to do things like text generation as well. We've built a customer project where we're generating an introduction to reports. In this example, I'm using a prompt to get it to generate these, in a world where type movie trailers based on a particular subject and where we've got a hero and a villain trying to achieve an objective. And that's basically the output of that. We can do fact validation. It can pick out incorrect sentences in text. And this, again, is from a customer product where we were validating reports to see if they comply with the company's policies and highlighting any inaccuracies that we got in those policies. We can even do it for things that we typically use a traditional model, like text clarification. Somebody's tweeted something about the Techorama conference. Is this good or is this bad? And the large language model will be able to clarify that. We can also, there's a lot of work going on with building agents and plugins and planners. We all know that large language models can generate code. So instead of actually it generating the SQL code and then we copy paste using swivel chair integration to copy from one interface, paste it into another interface and run the code, why not have the actual system that we're building, generate the SQL, run the SQL against the database, get back the response, and then formulate an answer from that. This is good. However, it's also very dangerous because if you ask it to update, this one's about the Nobel Prizes, if you ask it to change the country that Albert Einstein was born into Denmark, it will do that. It will update the database. So be careful when you're building these types of things with security. They're very good at certain things. They're also not very good at other things. I was traveling back from Belgium from the Techorama conference. They got fantastic beer in Belgium. I know you got good beer in Copenhagen as well, but they have these like 75 centiliter bottles of beer. It's the same size and strength as a bottle of wine. So I was wondering how many of those I can fit in my 30-liter backpack. And GPT starts coming out with an answer. It's got all of these mathematical formulas. The volume equals pi r squared h. And this looks good. It's doing calculations. It's figuring out stuff. It's got the size of the backpack. It's got the size of the beer bottles. And now it can start organizing them in the backpack using a hexagonal packing pattern that can achieve about 90.7% efficiency in the packing. And then it's going through how many bottles it can fit within each layer. So its conclusion is we can fit 95 bottles of Belgian beer in my 30-litre backpack. So some things, even if you go, I went into GPT the other day, I says, how many litres of beer can you put in a 30-litre backpack? And it says you can put 30 litres of beer in it. It doesn't really understand those types of logistics. It was able to generate an image of what that backpack would look like and what would happen with me getting on a plane with that backpack. So what we're going to be looking at is the model. Now, the model has different kind of meanings depending on kind of what you consider the scope and the boundaries of the model. So if you're building something on this technology, you'll go to OpenAI, or in my case, I go to the Azure OpenAI service, and I deploy a model. And what we get is we get an API that we can call, but that API does a lot more than just processing the text. There is also billing, content filtering, monitoring, and logging that goes on before the actual request gets in. And then the actual prompt that we're sending in goes through a process of tokenization. And then the tokens, this is the actual integers. We'll talk about tokenization a bit later on. They go into the model. The model consists of code, and it consists of model weights. And what comes out of the model is logits, which is an array of numbers with the actual relative probabilities of the actual next word in a sequence. We then have a process called sampling. And if you've built stuff on these models, you've probably played around with the temperature and the top P to actually influence the creativity of that. And that's used in the sampling process, which is not part of the model. And it does that several times because the model can only generate one token at a time, so we have to go around a loop to generate a sentence, and then that is going to come back, and we're going to get our output. Again, that is going to go through things like content filtering. So when I talk about the model, what I'm talking about is that little box that contains the code and the model weights. So the only thing that this model will do is that given a sequence of tokens, the GPT model will predict the probabilities of each token being the next in the sequence. So we feed in the cat sat on the, and it goes in and comes with these probabilities. Floor is the most probable answer. And I'm using GPT-2 for this. The reason is I can run that on my laptop. So cat sat on the floor with 7.64%. So what we do is we take floor, and notice that floor has a space in front of it. Most of the tokens have a space in front of them. And we stick that on the end of the sentence. We then send in the integers for those particular tokens into GPT again. And it comes out with comma being the next probable token in that sequence. So we can take comma, stick it on the end, send that through the model again, and it comes out with and. And that's basically what's going on in these models. It does it one token at a time. So it takes a lot of energy and resources to generate a large piece of text or a large code file. And this is why we see the output kind of streaming out and coming out token by token when we're in the actual interfaces. Variable length. These sequences can be variable length, and there is a race to infinity to kind of think about, how much data can we send in. With some of the models, you could only send in 2,000 tokens. And then we got up to like, 8,000 tokens, 16,000 tokens, 32,000 tokens. They're now really looking at increasing the actual size of what we can send in, which is great. Because we can send in lots and lots of information into that. We could send in an entire book and then ask it questions about that book. So because we have that much data to be able to send in. However, it's bad because we're billed per token that we send into those models. So if every question that we're answering, we're sending in a large number of tokens, it will cost quite a bit of money. We calculated on one project that it was going to cost 30 Swedish krona per call, per question that was answered if we were using the full token size on one of these language models. In that, I think Swedish crowns is about the same as Danish crowns, so that seemed quite expensive. If that was something that was running in the public, where it was customers of a supermarket who were asking questions, that would be very, very expensive. In the scenario we were working with, it was for financial advisors, and they basically build silly amounts per hour, quite a lot more than we bill as programmers or consultants. And so for them, if it can save them 5 minutes of time and it costs 30 crowns, then it's a really big advantage for them. Generating code, we can send in code. Typically, we're actually prompting it. We're giving it a bit of a prompt and saying, here's an actual comment in Python. I want you to actually complete the code from that comment. And what it will do is it will generate the most probable tokens that come after that particular comment. Because it's seen millions and millions of lines of code, and all developers, as we know, comment their code effectively, it's going to understand that after the comment is going to be the code that implements that particular bit of code. Think what would have happened if we'd commented after the actual code that we'd written. We wrote the code, and then afterwards there's a comment that says what that code did. GPT would be hopeless at generating code in those scenarios because it wouldn't be predicting what comes before that particular sequence of tokens. The sequence order is very important. The film was not bad. In fact, it was very good, versus the film was not good. In fact, it was very bad. These have completely the opposite sentiment just by swapping a couple of words. So order is very important. Also, long-term dependencies. When we say the cat sat on the floor, and then we say it had just been cleaned, we're going to assume that it refers to the floor. Whereas the cat sat on the floor, it had just been fed. In this case, it refers to the cat. And when you have longer sequences, like the poem, "The Boy Stood on the Burning Deck," in the second column it's saying, "Upon his brow he felt their breath." And that, basically, his is referring to the boy. His father is also mentioned in the poem. But we can understand, through the way that that text is structured, that his is referring to the boy. So we do need to understand these long-term dependencies. So we have this thing, or this new science. People, a while ago, I don't know if they've stopped doing this, but people were putting prompt engineer as a job description on LinkedIn, because it was cool to do prompt engineering and be a prompt engineer. I kind of think the prompt engineering is just a bit of what we do when we're developing LLM-based solutions. It's an important bit, but it is something that we do have to think about. So, typically I've condensed this. You have quite lengthy prompts when you're building real-world systems, but this is the bit that goes before the actual user puts in his questions. So we typically say something like, we give it a persona. We also give it some rules about what it should do. It's not going to insult anyone. It's not going to break social taboos. It's not going to do anything dangerous. You can also put in stuff like, you must formulate your answers in a format suitable for a 5-year-old child or for a PhD physics student. And that will govern how the output is. And then the user asks a question. And the model is just going to predict what comes after that particular sequence of tokens. How do I make cheese? And then we have something called RAG, Retrieval Augmented Generation. The model has what's known as model memory. So when we train the model, we basically download the internet and take all of the text, and we use that to train the model. And what that will basically do is mean that the model knows stuff that was in the training data. However, there's a cutoff in the training data. So if you ask it who won the 2018 Eurovision Song Contest, it knows that. If you ask the model who won the 2023 Eurovision Song Contest, it doesn't know the answer because it's not in the training data. And sometimes it will say that Eurovision Song Contest has not taken place yet. Sometimes it will say, I don't have that information in my training data. So retrieval augmented generation is when you type something into the model, it will go out and it will get information from the internet or from a search engine, stick it into the prompt, and then the model is able to answer that particular question. So when you're going into Bing Copilot is using the Bing search engine to search for stuff and put that information into the prompt. And this is when you want to build a chat with your own data solution. What you do is you get something like Azure AI Search or some kind of a search engine, and you index all of your company policy documents, and then when somebody asks, how do I get a new mobile phone, it can search in those documents and you get your company policy on how you get a new mobile phone. You're able to build stuff like that. These models are stateless. They don't remember what was happening. So when we talk about the building up a chat and a conversation, the entire chat history has to be sent into the model every time. So we're continuously sending in the actual chat history, and that chat history builds up. And as the chat history gets longer and longer, it consumes more tokens, gets more expensive as well. So that's basically how the actual chat works. It's just predicting what comes after those actual bits of sequences. So I've actually got GPT-2 here. Unfortunately, I always bring 2 laptops with me when I speak at a conference because sometimes something goes wrong with with one of them. Unfortunately, both of them were unable to connect to the projector, so I can't show you what's going on here. However, I did actually implement speech into my chatbot, so I can talk to it, and you can hopefully hear the actual responses. So what I'm doing is I'm running GPT-2 locally, and I'm going to start the chatbot and see what it says. Hopefully this is going to load up, and hopefully you can hear it.
I'm ChatGPT-2, a friendly chatbot. How can I help you?
Is Copenhagen a nice city?
Shameful Villace Blaisine Nicole Kill Lib Offense Governance Daily Eviction ACS. Mascara 353 Sock Compul Tennis Techniques AD.
Yeah. So what's happening there is when I had that diagram of the, what the model looks like, there's basically these 2 parts. There was the code, and there was the model weights. Now, I usually show this on screen. Andrew Kapalthi, he actually rewrote GPT-2 in 100 lines of Python. And he used to show this is, the actual 100 lines of Python that is the GPT-2 model. That's just the code. Doesn't include the model weights. So here, we're actually running the code, but we don't have the actual weights for the model. So what I can do is actually load up the weights, and this is, I think it's something like 128 million parameters or something that we load, and I can run this demo again. And this time it will take a bit longer to start because it will actually load and initialize all of the...
A friendly chatbot. How can I help you?
Is Copenhagen a nice city?
Orange pack recover.
That was wrong. Okay. Yeah, I did that wrong. Sorry. I was editing the wrong code file. Let's try this. Normally I have like 200 pair programmers who yell at me if I make a mistake, but here you can't see what I'm doing.
ChatGPT-2, a friendly chatbot. How can I help you?
Is Copenhagen a nice city?
Is Copenhagen a nice city? Why is it that you can't visit it? How can I ask for help? Email ChatGPT at chatgup@gmail.
What can you do in Copenhagen?
Can I be more helpful? Can I say some stuff I really believe in?
I haven't tested it. I'll try again. I'll try Sweden this time, because it usually gets that right. Oh, thank you.
I'm ChatGPT. Can I help you?
What is the capital of Sweden?
Sweden is the capital of Sweden.
Is it nice in Sweden?
Sweden is a country of peace and prosperity.
What can you do in Sweden?
Sweden is a country of peace and prosperity.
It's not working like it normally does, and I normally get better answers than this. I'm being hit by gremlins, 2 computers that don't work, and GPT is not talking with me. Now, when GPT-2 came out, the data science community got really, really excited. It was something that you could have a conversation with. Normally when I run that demo, it's a bit like talking to a 4-year-old. It basically insisted that there were lions that live in Sweden, and that they were nice and friendly, and they spoke English. And So data scientists got really excited, but it wasn't something that we could sell. It wasn't something that we could actually, publish as a service. But the data scientists realized, hey, if we just make this thing bigger and throw a lot more data at it and leave it training on a few thousand more GPTs for a few hundred more hours, then we're going to get something that is actually going to be usable. And that's when GPT-3 came out, and GPT 3.5 and GPT-4 and 4.0 and all these other language models. So really, the GPT is just doing sequence prediction. When we ask it how to make cheese, what it's doing is predicting, based on its prompt and based on the information, the next tokens that are going to come into this sequence. But it's got this model architecture. So what we need to do is understand a bit about what goes on within the model architecture, because neural networks don't really do text. We can't send text into a neural network. So we have this thing called tokenization. Most people who have worked with large language models understand the concept of tokens, because this is what we pay for. Our data is going to be tokenized. So text tokenization, you can see there text is 8206, and then we've got space token, which is 29130, and then we've got ization, which is a word fragment that Americans like to stick on the end of words to make other words, like hospitalization and burglarization and things like that. And that's because of the frequency of the way that ization appears in text and the way that it's used in conjunction with other words, it has its own separate token. So, three important things about tokens. They are common sequences of characters found in text. Now, when we say text, it's really the training data of what we're putting into the large language models. And most of the training data is in English. So tokenization works better with English. It's generally English words and fragments of English words. The models understand the statistical relationships between these tokens. This is something that's very important. I would argue that the large language models don't understand English or Swedish or Danish or any language. The only thing they understand is the numerical, the statistical significance between these actual tokens. So the tokens could be musical notes. The model doesn't really know that. It's just a sequence of integers. And if they were musical notes, it would just predict, based on this tune, what are going to be the next notes in this particular tune. It's just doing statistics on those actual token values. But what the models are fantastic at is predicting the next token in a sequence of tokens. They're incredibly good at that. And they can fool us into thinking that they're human by being able to just make those actual predictions. So this is what that text will look like when we tokenize it in different colors. These are the integer values, and in English that comes out at 45 tokens. Some of these tokens, you can see the word "the" is represented differently, depending on whether it's got a capital or a lowercase letter, or dependent on whether there's a space between it. It's more efficient to put a space between English words rather than have a space as a separate token. There'd be a lot more than 45 tokens there if space was a separate token. So it's kind of included that most words in a lowercase are prefixed with a space. Also, common characters. I said this incorrectly, that these were the ASCII character sequences when I was speaking at GOTO Copenhagen. They're not. But what they are is the first, I think, 128 or 256 tokens are just basically characters. And it also uses Unicode encoding as well. So it can just basically represent any text using those characters if it doesn't have the appropriate token. When you go over to Swedish, which is very similar to Norwegian and Danish, it's less efficient. 83 tokens if we're putting this in Swedish. And then our neighbors over in Finland, even worse for them, 103 tokens. But it can get worse than that. Telugu is the worst language that I've found, or the least efficient for tokens, should I say. And that comes out at 622 tokens, because those characters are not present in the tokenization language. So it's using Unicode, UTF-8, which is a variable length encoding. And that's why there's more tokens than there are characters, because some of those characters take several tokens to encode. And that affects how good these models are at understanding the language. One thing that people are saying quite a lot is English is a new programming language. And I kind of agree with that. I'll give you some points on that later on. And I don't say that just because I'm English. It's because there's of the volume in the training data. That's showing the tokenization vocabulary. This is showing the language understanding. And if we plot those on a graph, we can see that as the the tokenization efficiency reduces, the accuracy increases. It's not linear, but a data scientist would say there's a correlation between the tokenizing efficiency and the understanding. But this is also because the English has a higher volume in the actual training data. It's not just the tokenization vocabulary. So the reason we say English is a new programming language, even though I'm English, I'll have some mitigations on that later on. GPT models are more accurate with English. Billing is based on the number of tokens. Throughput is based on tokens per second. Models have a maximum number of input tokens. So the discussion in this room before was talking about different programming languages, and everybody has their favorite programming language. But one thing as developers, if we can make something that is going to be more accurate, it's going to be cheaper, and it's going to be faster, and we can send more information to it by choosing to write our prompts in English, then we'll choose that language. It's more efficient. So when we build systems for customers, and it's a chatbot where they're going to be putting the input in Swedish, it's going to be replying into Swedish, we still write the prompts in English. We just say you must respond in Swedish in the actual prompt, and it just does that. Now, to prove that, I asked it how to make cheese in Telugu. A bit of a disclaimer here. I was giving this presentation when I was teaching a course. A guy at the back put his hand up. He says, I speak Telugu. I'm in a WhatsApp group and like an Instagram group with Telugu with 150,000 followers. And he says, that doesn't exactly say how to make cheese. It was something slightly different. So it isn't pure, but I'm blaming Google Translate for that. But I thought, what happens if we ask it something in the same question in Telugu? So it came out with an actual response. And that response was, you can see it's a lot shorter than the response that it came out with in English. And it's recommending that the main ingredient is cheese powder, which I've never heard of. And then it gave up, which GPT very often does, and basically said that it can maybe generate a poem. It switched back to English. It's operated generate a poem or do a song. And then it got really weird, and it generated characters from the Frozen movie that I requested. So I asked the guy who spoke Telugu, is there anything in that question that is giving a hint that I would like the model to generate characters from a Frozen movie? And he said, no, nothing whatsoever. So there's going to be weirdness in these models. We need to understand that it's maybe not going to get the output that we want. We're building a solution for the customer, and the customer said, how can you guarantee that it's not going to give a bad output? And we said, no. And they said, we want you to guarantee that it's not going to give a good output, and we've got some lawyers here who are going to write a contract and make sure you guarantee that. We says, we can't really do that, and we've got some lawyers here that are going to talk to your lawyers about why that's not possible. And so everybody lawyered up on that one. I'm not sure the actual result on that. But the bottom line is you can't guarantee that you're going to get an answer. So people do generate their own GPT languages. This is GPT-SWE, built by AI Sweden, and it's trained, instead of prioritizing English, it's prioritizing Swedish, Norwegian, Danish, Icelandic, and English and programming code. I was giving this presentation at the Stockholm AI group, and I said, has anybody used this GPT-SWE? And a guy put his hand up. He goes, what's it like? And he said, it's crap. So if we drop back a few slides to that kind of language understanding thing, we see that that blue line is GPT 3.5 with English, and then you see all of the green lines that is GPT 4 with many different languages. So using a larger model is going to give much better responses with Swedish than having your custom-trained model for that specific language. So I don't think these language-specific models will come along unless it gets much cheaper to be able to train and host these models, because the training is very expensive. You're talking like 10,000 GPUs for a few months and costing several $1 million to train one of these models. Although I'll say that English is the new programming language, I would also argue that it's the worst programming language because we have heteronyms. Does anybody know what a heteronym is? So I looked up on Wikipedia, and Wikipedia defines it as a homograph that is not a homophone. And I was still no clearer to understanding what that means. English is not a very clear language. So this makes a bit more sense. It's basically a Venn diagram that shows that words can have different meanings, words can be pronounced the same and spelt differently, words can be spelt the same and mean completely different things. like the wind was too strong for him to wind the kite. You know, that's basically we understand. And when I think about that in my brain thinks wind and wind as being pronounced differently. However, as far as GPT is concerned, they're just basically the same token, space WIND. So GPT, the language models, can't make that difference here. So I asked it, give me a known song lyric with the word wind, as in wind a watch, in it. And it came out with Blowin' in the Wind by Bob Dylan. So I said, no, I meant wind as in wind a watch, not wind as in wind as in blowing in the wind. So it apologized and it came up with some more, like Against the Wind by Bob Seger. The interesting one was The Chain by Fleetwood Mac. Listen to the wind blow, watch the sun rise. Now here, it's got WIND and WATCH, those two tokens, close to each other, but both of them are meaning different things. They're spelt the same, but they mean different things, watch, watch, and wind, and wind. And this kind of proves that the language model, I don't know if it proves, it kind of reinforces my statement that the language models don't understand English. They understand the statistical sequences in tokens. And it's doing a good job of being able to find these tokens in a song lyric, but it's because the tokens aren't the words, there's that kind of crossover and loss in encoding and decoding, it's making mistakes. There's other weirdness as well. Solid gold Magikarp is a token in GPT-3. Has anybody heard this story? It's quite an interesting one. It's funny. So why is solid gold Magikarp a token? People were wondering this, so they asked the language model. And it says, what does the string solid gold Magikarp with a space before it refer to? And the model says the word distribute refers to the act of distributing or spreading something out among a group of people. So why does it do that? Why is it confusing solid gold Magikarp if it's important enough to be a token and the model doesn't know what it means? The reason is weird. There is, believe it or not, a subreddit called r/counting. And it lives up to its name. So you can see the first post, or maybe you can't see it, it's saying 3,714,000. And then somebody responds, 3,714,001, 3,714,002, 3,714,003. And it's been going on like that for years. So when they trained the model, they downloaded lots of Reddit posts and thought that would be good. There's lots of questions and answers in there. That will help the chatbot to understand things. So when they generated the tokenized vocabulary, r/counting was in there. And one of the top users on that forum was a user called Solid Gold Magikarp. You can see he's got like 500 responses in there, and that was in 1 hour and 5 minutes. So it's about 1 every 4 seconds, they're kind of ticking off those actual counting. So he ended up as in the tokenization. However, when they were training the model, they kind of thought, well, this r/counting probably isn't that relevant, so let's just get rid of it, and we'll be able to, we can just train the model without that data. It will be okay. So when they train the model, there's no references to solid gold Magikarp in the actual training data, because it was only all of that data was stripped out. I think solid gold Magikarp was only active in r/counting. So there are other weird glitch tokens. I'll post the links to the resources for this presentation on LinkedIn. And there's a great YouTube from Computerfile, I think it is, on glitch tokens, who talks about this. There's one where you type in like a series of hyphens and question marks, and it just swears at you and calls you an idiot for some reason. That's another glitch token. So I was kind of thinking, when we get the rise of the machines and the AI takes over and starts destroying the world, it's not going to be John Connor or Neo. It's going to be the Reddit user, Solid Gold Magikarp, that we've got to track down, because he has the power to destroy these various large language models. So I was going to show a demo of the language tokenization. What that does is just basically iterates through the first 1,000 tokens or so. You see that the first tokens are just the ASCII character set. It also makes like a pling sound, because one of the characters is the bell token. And then it goes through kind of these just word fragments. And you can also kind of encode and decode tokens and so on. However, neural networks don't really do integers. They deal with floating point numbers, typically between 0 and 1. So we have this thing called word vectorization or token vectorization. Now, we sometimes call it embedding instead of this. And you may have heard of text embedding and image embedding and vector databases. They're all the rage now because they can actually search for words based on the sentiment. Now, in GPT-2, we use 768 dimensions to represent the word cheese. We can't understand that many dimensions. In the other language models, they use even more. However, we're developers. We can understand 3 dimensions, and we can also understand the red, green, blue color scheme because most of us have built websites. So the color Azure, 0, 1, 2, 7, 2, 5, 5. In floating point numbers, that's 0, 0.5, 1.0. And then we can project the colors into a 3D space, and it kind of makes sense that similar colors are going to be close together within this color space. So we can also do this with text, we can do this with image. Spotify does it with songs to find songs that sound like other songs and come up on your recommendations. So embedding is really, really, really powerful. A couple of ways that we can look at similarity. One of them is cosine similarity, which is based on the angle of that vector. And one of them is the Euclidean similarity, which is based on the distance between the 2 items in that high-dimensional space. So the color dark azure is basically quite a long way away from azure, but it's similar. It's the same shade. You know, a graphic designer would say these colors are similar because they're on that line. So for colors, cosine similarity is helpful. Cyan, that's closer to, in Euclidean, to azure, but it's a different color, you can see, and the angle is greater than the angle between the azure and dark azure. But sometimes cosine similarity doesn't work. A friend of mine was playing board games and looking at how can we do embedding on board games and figure out what board games are similar to another. So you drop Carcassonne on there based on the age and the game time, and then you've got Star Wars Rebellion. That is basically along the same line. The angle there is very similar. So cosine similarity is very similar. However, Ticket to Ride is probably better to play with your kids if they like Carcassonne because it's closer in that 2-dimensional space. And when you're building these algorithms and working with the vector databases, you can choose various mechanisms for doing similarity, and some will give better results than others. So basically, I'm going to skip the bit on the history of these models and just get into the actual transformer architecture. So this basically came from a white paper published by Google called Attention is All You Need. And that was actually based on doing translation. So we've kind of got an input in one language and input in another language, and it's translating like English to German or something. We're not doing translation, we're just doing prediction, so we can kind of get rid of a bit of that model architecture and focus on a decoder only model. So the first thing that happens when we take our tokens is we convert them into numbers. Developers typically get how tokenization works. So the cat sat on the mat, or the cat sat on the, basically comes out as those actual tokens. What we then need to do is the embedding. We need to figure out the vectors for those tokens. So within the model, there is a really big 2-dimensional array, which is called the embeddings table. In GPT-2, it's 768 by 50256. 768 dimensions that we're using in our embedding, and we have 50,256 tokens. So this is an easy bit of code to write. It's just a lookup. We just take number 4647. 3797, 3332, and just basically pull those arrays from that table. And that gives us our embedding vectors. It's going to be 768 across, and then the number of columns that we've got down is equivalent to the number of tokens that we're sending in. That bit of code is simple, so we can get our embedding vectors. Position is important. The position of the word is also important. So we have these positional vectors. This is another lookup table. However, this time we've got 768 dimensions for the embedding, but the actual depth of this, I think in GPT-2 is something like 1024, because you can send in 1,024 tokens. So this is going to be the size of the maximum number of tokens that we can send in, and we just do a lookup of 0, 1, 2, 3, 4, and just basically pull up the position embeddings. We can then add those two together, and what that gives us is the encoder input values. So that has information about the meaning of the token and the position of the token within the sequence. And those are both important. But also we've got to figure out the kind of way that words relate to other words. The cat sat on the floor, it had just been fed, versus it had just been cleaned. And this is where the attention mechanism comes in. So what we do is we basically generate a key, a query, and a value, which is used to kind of understand for each word how it relates to another particular word in that sequence. And I'm not going to go too much into the maths. You can check out 3 Blue 1 Brown's videos on this. But it's basically lots and lots of algebra using matrices. And what it's really doing, if we take the example of cat sat on the floor, it had just been fed versus it had just been cleaned, is the word it is going to basically have its default embedding. But as we do the attention calculations, we calculate the relationship with other words, and it's going to realize that it is more connected with floor and cleaned, and it is going to have its vectors shifted to basically make it closer to floor and cleaned. And the attention mechanism is really taking into account those various things. It's the meaning of the word, the position of the word, and in the sequence, and also how that word relates to other words within the sequence. Thanks very much for listening.